Hi, welcome. In this video, we're going to be talking about the concept of independence of two events. I just want to remind us of the conditional probability formula that we were working on in the previous unit. So probability of B given A is equal to the and probability of A and B divided by the probability of A. Okay, so we're going to put that on aside. That's a general conditional probability formula. So we're going to jump right into the definition of independence. Events E and F are independent if the occurrence of event E does not affect the probability of event F. So we can write that in formulas as the probability of F given E, that is the occurrence of event E. Suppose we know event E occurred. So the probability of F given E is equal to the probability of F, because the occurrence of E does not affect the probability of F. So that's how we write that in equations. And here we have the probability of E given F is equal to the probability of E. So if we're given independence of E and F, then both of these will hold. Notice the difference between the conditional probability in independent events and the general definition of conditional probability. Okay, just want to go over to the notes for a moment. So some examples of independence: flipping a coin and getting a tail, we could call that event E, and choosing a card and getting the 7 of clubs, we can let that be event F. So E and F are independent because when you flip a coin and you get a tail, it doesn't affect the probability of choosing a card and having that card be the 7 of clubs. So also, let's see, choosing one student at random from University A, let's call that event E, and choosing another student at random from University B. So if it's two separate universities, two separate random samplings that are not connected in any way, then those would be independent events. And choosing a card and having it be a heart, event E, and having it be a jack, event F. So that one's a little more, we'll look into it because it's not as obvious, but you know, we can get into that. So the opposite of independence is dependence. Two events are not independent, then they are said to be dependent. Dependent events, excuse me. Dependence doesn't mean that the two events completely rely on each other. It just means that they're not independent. The occurrence of one has some effect on the occurrence of the other. It could be a small relationship. It doesn't have to be completely certain. So suppose there are two roommates, Jack and Joe, and Jack took his umbrella, let that be event E, and let F be in a given morning on a given day. Jack took an umbrella to school, and then his roommate Joe took an umbrella. We'll call that event F. So we might not consider these are likely dependent events because the decision for Joe to take that umbrella might have something to do with what he saw his roommate do. Okay, a couple of other events that are dependent: choosing a card and having it be a heart, having it be a red card, we'll call that event E, and choosing a card and having it be a heart, we can call that event F. So if we know that E occurred, it certainly changes our probability of F. So if we know it's a red card, right, half the red cards are hearts. So if we know it's a red card, then the probability of a heart given a red card is gonna be 1/2. In general, if we didn't have any information on the color of the card, that is, if E was unknown, then the probability of a heart's going to be, it's a quarter of the deck is in each suit, so 1/4. And then also the number of people at a party, and we'll call that event E, is not independent of the noise level at the party, event F. So another concept I just want to make sure we separate is this disjoint events, which we discussed in the previous in the beginning of chapter 4, disjoint events and independent events. Okay, so I'm going to go to the whiteboard and quickly just draw a picture of dependent events. I'm sorry, rather, mutually exclusive events. So we'll let A and B be mutually exclusive. Here is A, and here is B. So if A and B are mutually exclusive, and we know that A occurred, we certainly have information about the probability of B occurring, right? Because they can never occur together. So that's mutually exclusive events are always dependent. So I wanted to talk about multiplication rules. We have a general multiplication rule for any two events. The probability of E and F is equal to the probability of E and F times the probability, the probability of E and F equals the probability of E given F times the probability of F. Okay, I'm going to take this over to the definition we've been using for conditional probabilities, and note that really all we're doing here is dividing by the conditioning events. So in the A and B case over there on the board, we multiply both sides by P of A. We would get P of A and B equals P of B given A times P of A. So here we are. That's just written with the E and F event labels. Okay, so for any two events, this is true. And in contrast, we have a multiplication rule for independent events. If E and F are independent, then probability of E and F is probability of E times the probability of F. Okay. That follows pretty directly from the definition of independent events. So if I knew E and F were independent, then E given F is the same as P of E. And that's why these two, this is for the general all events, and this one is multiplication for independent events. All right, so I wanted to give an example and see how this works. If we choose 2 cards from a deck of cards, 52 cards, without replacement, all right? So then, if we let E be the first card is black and F be the second card is black, we can see that once we choose a black card in the first draw, then the probabilities of choosing a black card in the second draw have shifted because that first card is no longer in the deck. So we have, let's look at this, the probability. Let's find the probability of E and F. And that is the probability of E, first card, times the probability of F given E. Okay, and so the probability of choosing a black card in the first draw, there are a total of 52 cards. 26 of them are black, so it's 26 over 52. And now the probability of F given E. So if we chose a black card and we didn't put it back in, the total number of cards in the deck is 51 in the remaining deck. And the total number of remaining black cards is 25. So this is the probability of choosing a black card. The first card is black and the second card is black. And this is without replacement. So we get 26 over 52 times 25 over 51. Okay, let's go ahead and talk about the situation. It's a different experiment. In this experiment, we're going to replace the first card. Okay, so we have the same two events. Event E is the first card is black, and event F is the second card is black. And we are looking for the probability of E and F, that both cards are black. Okay, and because we have independence, this is the probability of E times the probability of F. So the probability of E is choose a card, and it's black on the first draw. It won't matter that it's the first draw because the deck looks exactly the same on the second draw as it did on the first draw. But there's a total of 52 cards. 26 of them are black, so that's the probability of E. And the probability of F is the same because we're looking at the probability of drawing a black card, and the deck is looking exactly the same. Okay, and so we should know that these are not the same. In fact, choosing a black card, knowing that you chose a black card in the first draw, if you're not replacing it, changes the probability of a black card in the second draw. So without replacement is an example of dependent. It's an experiment that yields dependent events, and with replacement is there the events. Most of the events we'd look at would be independent. We're looking from trial to trial. Okay, so sharing the screen on the notes again, I wanted to talk a little bit about computing an at least probability. So first of all, what do we mean by at least? So suppose an experiment yields a non-negative integer. So the integers could be 1, 2, 3, 4, 5, like that. For example, at least 1 means 1, 2, 3, or 4. At least 5 means 5, 6, 7, or 8. One of my colleagues told me he thinks about it as if he told his students bring at least $15 to school tomorrow to buy a sweatshirt, they could bring 15, they could bring 20, but 10 won't be enough for the sweatshirt. So at least means you start with that value and move upwards. So calculations can be like, if we want to go directly to calculate the probability of at least 1, then that would be the probability of 1 plus the probability of 2 plus the probability of 3. If what we're doing is if this experiment yields that non-negative integer. Okay, so we would have to add up, we would start with 1 probability. So here's the event 1, 2, 3, or 4. So probability 1 plus probability 2 plus probability 3, so plus probability 4, and that's a lot of probabilities to calculate. So for at least probabilities, we often lean on the complement rule. So that is that let the event E be at least 1, and we want to calculate the probability of E, but we're going to find it a lot easier to focus on E complement. So E complement is the complement of E, and non-negative integers, I should have started with a non-negative integer is 0, 1, 2, 3, 4. I might have misspoke, but integers start at 0. So E complement is the event that when E does not occur, and so it's going to be exactly 0. So it might be easier to calculate the probability of exactly 0 and get to the probability of E as 1 minus the probability of at least 1 as 1 minus the probability of 0. So let's go ahead. I have an example here. So we flip a coin 5 times. What is the probability that we get at least 1 head? So E is the probability of at least 1 head, And then E complement is no heads. So that would mean all tails. So we'll look here, the probability of E complement. E complement, it can be described as tails on the first flip, tails on the second flip, tails on the third flip. So fourth flip and fifth flip. So since the events are all independent, that is the results of what happened in the first flip of the coin does not affect the probability of a tail in the second flip of a coin, then we know that the probability of E complement is a half times a half times a half times a half times a half. And hence the probability of at least one tail is the probability of E is going to be 1 minus 1/2 to the fifth, or 1/32.